In this video, I'm going to show you how to prepare training data for deep learning in just a few seconds. Unlike traditional computer vision images, that's only PNG and JPEG. So geospatial data can come with a variety of formats, including raster data and also vector data. So this is just a simple example. If you want to train a building detection model, you usually have imagery, and you also might have some annotation, for example, building label like this. So you might have a one single imagery and also one annotation vector data layer, or you might have one multiple images, for example, or smaller tiles, and have one big single vector data, or you might also have individual. So for example, here I have two images and I have two. So this is just an example. You might have hundreds or thousands of images, and you also might have hundreds of thousands of vector labels. So how can you create the training data for deep learning? And this is what we're going to cover in this tutorial. And we're going to use the open source GeoAI Python package. And it's super easy, only takes you a couple seconds to create the image chips so that you can easily feed the data into deep learning. So let's get started. To follow through, you will need to download the novel example from the OpenGeoAI website. So the link is also in the video description below. On the left side, click examples and then scroll down to find create training data. So if you click the create training data, then you can either run this one using Google Colab. So just right click, open in Google Colab, and make sure you change the runtime type to GPU. So click change runtime type and then select T4 GPU and then click save. Then you'll be good to go. You need to make sure you install the package. I think I forgot to add that. So you need to click here and then just pip install GeoAI Python, and then just control enter. Then you will be able to install the package on the Google Colab environment. Alternatively, if you have installed that on your local computer, you can click the link and then right click save as. You will be able to save this one to your computer. Then you can run that on your local computer. So I'm going to show you step by step how to run this one on a local computer. But again, you can run it on Google Colab if you want to. So I have three different scenarios. As I mentioned earlier, you can have one raster, one vector, or you can have multiple rasters, one vector, or you can have multiple rasters and multiple vectors. So those are very common scenarios that you might counter with geospatial data when you're trying to do deep learning. And also you might have multiple rasters and multiple raster masks. So that one we already covered in a previous tutorial, but you can also check out the link here. There will be two other tutorials, creating image chips or image tiles. So image chip basically just one imagery, one mask. Image tiling, the novel example is multiple images and then multiple masks. So basically just the raster data. For today, we're going to cover vector data, vector annotations. And so here, we're going to go through step by step how to create the data in seconds. Very, very easy. So first, let's import the library. Just import OS and import GeoAI. Then we're going to download some sample data. So here, I have put some sample data on Hugging Face. So all I need to do is just to run this code block. It's going to download the sample data from Hugging Face. So inside, you're going to find images. So there will be two National Agricultural Imagery Program, basically two image tiles. And then we have mask 1 and 2. So let me show you here. I'm actually going to open the data so that you can take a look at what's inside. I'm going to be very clear. Oh, I can also open here. Let me show you docs examples. So after you download that, it's going to basically unzip. So if you look at this here on the left side, these are basically the images within the zip file. So we have two images, tile 1 and tile 2, just like what I showed you earlier in QGIS. We also have mask 1 and 2. Mask 1 is just a single vector file covering the entire area, and mask 2 has two separate image GeoJSON tiles. Basically, one GeoJSON covers one image, and so we have two images, we have two GeoJSON. So we have these three directories and containing all the files that we need. So next, let's take a look at what's inside. You can explore the data. I can run this code block to see all the content. Like I said, we have two images, one mask, and also the other 2 masks. So single mask or multiple masks. And this is data that we have. So first, you can actually look into the data inside. We are going to use, for example, just the first image type and also the first GeoJSON. We are going to call this display image with vector. So this is a kind of a utility function that allows you to quickly see what the data looks like. So if you run this code block, it's going to generate this result here, showing you the imagery and also the vector annotation overlay on top of the raster. So we have the building in red color overlay on top of the raster. So you can change it to the second one. For example, this is just tile 1. We also have tile 2. You can do it as well. So run this code block. This will generate another annotation here, and it's very simple and easy to use. You can use desktop.js, you can open QGIS or ArcGIS if you want to, but we have the function that allows you to do everything within the Jupyter Notebook environment. All right, so this for the data visualization. Next, let's try to create the image chips for deep learning. So all we need to do is just call this function, export GeoTIFF tiles batch. So this is just one single function allows you to handle different scenarios. The first one is image directory. So as I mentioned earlier, if you go to the left side here, we have this images directory that has 2 image tiles. And then we have the mask file. If you only have a single vector data covering all the images, then you want to use the mask file. But if you have multiple, then you want to use the mask folder. So folder means you have multiple. Mask file means you only have one single vector, and then specify where you want to output the data to. Where do you want to output the mask to? And then the tile size. So it's usually 256, 512, or 1024. It's up to you, depends on the size of the object that you want to detect. Also, the stripe basically means the moving window. If you have a tile size 256 and then you're going to move from the left to the right, from the top to the bottom, 256 means basically there's no overlap. So it depends on what you want. If the image tiles that you have, for example, this 2 image tile, you already have some overlap, then here you don't really need overlap. But if there's no overlap, then here you can change the, for example, the stripe to 128. So that means you're gonna have 50% overlay or 64, 25% overlay. So it's up to you. I'm just going to use 256. That means I don't need overlap. Also, you have a class unique value. So this one depends on your vector data. Right now, we only have buildings. So it's binary data, 0 and 1. But if you have multi-classes, for example, trees, buildings, vegetation, something like that, then you want to have a column in your vector data indicating what class it is. So here, by default, it's going to use the class. But if you don't have that, it's going to basically just converting the vector data to 0 and 1, just a binary raster mask. And then whether you want to skip empty tiles or not. Empty tile means if you're trying to detect a building, you only create the image chips. If that image chips does not contain buildings, it's going to be skipped. So it depends on what if you want to include the empty tiles or not. Max tile, so this one you can set a number. By default, it's going to generate all the tiles. If you set 20, that means each image tile is only going to get maximum 20 tiles. So this is for demo, so we're going to speed up the process. And whether or not do you want to be quiet or not. If it is quiet, it's going to be doesn't print out the whole process. So false, that means we want to see all the details. So that's it. Let's run this one and then take a look. Should be pretty quick. It's going to go through all the image tiles that we have. So one single mask file, the GeoJSON, it contains 735 features, and they have 2 image tiles. Then you're going to process them. So we're going to go through the process. At the end, you're going to also print out the summary, right? So the total number of image 2, and then they're all processed. And for each total tiles generated, 40. The reason for that is because we set the max tiles to 20, and so we have 2 images, then you're going to generate a total of 40 and then percent 100%. So if you go back to here, if you say quiet to true, that means it's going to be just print out just a small summary. You can also change the max tiles, comment it out, that means you're going to generate all the tiles. So they see how many, This one probably is going to generate, you see right now, we're going to generate 54 tiles compared to earlier only has 40 and 100%. So that's a good sign. So this is this one scenario that you have two image tiles, and then you only have one single vector data label. Then you can use this one to generate the image chips. So let's take a look at the result. So I'm going to go to the examples, and then it's under the output. So from here, measures one single mask. This is what just generated, and then images. So you'll be able to see these are all the image tiles that have been generated, and also the corresponding mask. So just a single line of code, just one function call, and you can create the image chips in seconds. Very, very easy to do. So this is scenario one. Scenario two is that you have multiple images, you have the also multiple vector files or multiple annotation file, and so in this way we're going to use the mask directory instead of mask file, because you contain multiple, as I mentioned. So let me go back to the example here one more time. It's under the NGB raster tiles, and then data mask. So right now we have two GeoJSON files covering two image tiles, and so all the other parameters pretty much similar, except that this line is different. So it depends on whether you have a single file or you have multiple file. Then we can run through the same process, just execute it and take a look. So we generate the same number of tiles, 40 tiles for demo. If you want all of them, just comment out this line and then run this again. You should be able to generate all the tiles. So again, it's 40 tiles altogether. So this is the second scenario. And so for this scenario, the file name do not necessarily have to be the same. Sometimes you might have different file name convention for your data. So for the images, so for example, the images is named like this, NAIP underscore RGB train underscore tile 1, right? So if the file name are the same, then it's great. If it is not the same, you can still do it. It's going to basically sort all the file names and then make sure that you have the same number of images and also the same number of vector annotation files, and then you should be good. But if this doesn't, is the file name not the same, then you use the second method. So basically second and the third, they are pretty much the same, like handling different cases. You can just, it's the same function. So the third one basically means the file name match each other. So the same file name for the mask as for the images. And so I can run this one, same thing. I'm going to run through it. So I'm going to generate 54 tiles as well. That's it. So as you can see, we can now handle so many different scenario, right? Whether your mask raster dataset or it's a vector dataset, or you already have one or have multiple, it's the same. So just one function can rule it all, and you can generate the data in seconds. So once we have the image tiles, now you can also take a look at that. Okay, so earlier this is the scenario number one, right? Measures one single mask. You can call this function GeoAI.display training tiles, and then passing to the output directory. So make sure your directory has like images and masks. So I have two subdirectories. So let me go back to the sample data that we generated, okay, under output. And then from here, this is measure number one. So make sure that this directory has two subdirectories, images and masks. And if you have that, then you can just pass in the root directory and specify the number of tiles you want to see. Just run this single line and take a look. Now we have all the image tiles nicely displayed here on the map, right? So we have the image, each image and the corresponding mask. So as you remember earlier, we actually have a vector building vector file. It has been automatically converted to raster and also do the reprojection if needed. So basically, if your image and your vector data, they don't have the same projection, you'll be reprojected to the same projection, and then it's going to cut into smaller tiles. And this is what it looks like. So you have 6 tiles, or you can maybe show 4 tiles. So you can adjust the number of tiles easily. So this looks pretty good, right? So we have one buildings, and the white color here represent the building footprint. So you have all of them here, and this looks good. So this is a quick way for you to check if needed. And so this is how you can generate the tiles. Of course, you can continue to generate other as well. So you can have more fine control if you want to. It's the same function. So this one, for example, you have 2 images, and you have just one single vector data. And so the type size, for example, 512, I'm going to have 50% overlap. You also can have a buffer radius. So the buffer means that if you are trying to detect, for example, rows or some other linear features, then if your vector is only just a single line, you probably want to have a buffer. Otherwise, you want to have some disconnected lines, and then the detection result is not going to be very good, because you need to basically have at least 1 or 2 pixels for each feature. And so other than that, other things remain the same. So here we're going to definitely generate more tiles. So right now you can see 50% over there, and the number of tiles. You can also display them. So let's see the differences. I can copy this line of code here and come back to this one, paste here, but you need to change basically the raster path to this one. So output advanced example, and let's see if you can see the tiles. You will notice the difference because we have some overlap, and we also kind of buffer a little bit. So you can see right now for this portion, right? So for the first image and the second image, you can certainly see there's some overlap, right? So on the right side here, this portion kind of also overlap with this portion, right? So 50% overlap is basically how you control. So this is certainly important. If your original image they do not have overlap, then when you generate the image tiles, you need to make sure that you have the stripe have some kind of overlap, and also the buffer radius. So basically like 0.5 meter buffer. You can increase the last number if you want to. So for example, this increase to maybe 3 meter buffer. So for the buildings, we usually don't need that, but for roads or street, something like that, you certainly or power lines, for example, you certainly want to have a buffer. Okay, it's done. Now let's visualize the data again, and hopefully you're going to see the building, right? So now you can see the building. It certainly looks a little bit larger because we buffer a little bit. Again, just adjust the parameters a little bit, and that's all. You don't need to do a lot of complicated operations. Once you have the labels, now we can start changing the data. So I've covered this in some of the previous tutorial, but here I just want to show you the step, right? So once you create the images, then we can pass this one into the deep learning model. So just call the train segmentation model function, and then passing the image tile. So this is measure number 3. If you can see here, we have output, right? Measure 3. That means the file name, they match with each other. And so we have the same number of images. We also have the same number of masks. Once you have that, we can specify what architecture we want to use. We're going to use, for example, the UNet architecture, and then the ResNet 34. Also, we're going to use the pre-trained weight ImageNet. And so other parameters are very much similar to our previous tutorial. 3 RGB channels, and we only have 2 classes, building and non-building. Base size 8, so basically means we're feeding 8 image tiles all at once into the model, right? So here we have 4, basically have total 8, and then because we have 54, then 54 divided by 8, so that means you need like 7 batches to actually finish 1 epoch. And we train 20 epochs, learning rate 0.01, and then val split 0.2. That means 20% for validation, and that's it. So just run this one, and it's going to basically loop through all the 44 images. And so 43 for training, 11 for validation. And so I have 2 GPUs, going to use the 2 GPU for training, and you can see the process. So in general, you want to see the IOU increases, otherwise your model is not performing, because you want to basically have a higher percent of overlap between your prediction and also the ground truth. Okay, so it's done, only take a couple seconds. Now we have the final IOU, so it's 0.90. It's not bad, right? So we only have 54 image tiles, and then it already have a pretty decent accuracy. one last step, you can plot to see the performance, right? So here we show you the IOU and also the dice score. The dice basically means the F1 score. So we also have the loss, and this is exactly what we want to see. You want to see your model, the loss is decreasing, and the IOU and F1 score, they are increasing, and this is good. So you can train more epochs, so to get a higher accuracy, and then you can apply this one to run inference. As I mentioned, if you're interested, you can check out other tutorial here, how to train the model, and then how to basically apply the segmentation model to do object detection. Okay, I think that's all for this tutorial. I hope you find it useful. I will see you in the next one. Take care. Bye bye.